unveiling the universe's instruction manual, Newton's laws. Hey everyone, welcome back to the channel. Today, we're diving into the mind-blowing world of physics with a look at Newton's 3 laws of motion. These laws aren't just some dusty equations in a textbook, they're the fundamental principles that govern the motion of everything around us, from the smallest atom to the largest galaxy. Sir Isaac Newton, a pretty bright guy back in the 17th century, figured out these laws, and they've been blowing minds ever since. We're talking about the laws that explain why your coffee stays put until you lift it, why that baseball you threw eventually comes back down, and why rockets need so much firepower to escape Earth's gravity. So, buckle up as we explore these laws, using simple examples and cool animations to make them crystal clear. By the end of this video, you'll be seeing the world through the lens of physics, and trust me, it's a truly awe-inspiring perspective. All right, let's kick things off with Newton's first law of motion, often called the law of inertia. This law is fundamental to understanding how objects behave in our universe. This one states that an object at rest stays at rest, and an object in motion stays in motion, moving at the same speed and in the same direction, unless acted upon by an external force. It's like the universe's way of saying, hey, if you want to change something, you better put in some effort. Think about it, that book on your table? It's not going to suddenly zoom across the room unless you give it a push. That's inertia. It's the reason why you have to actually get up and push the book if you want it to move. It's the tendency of an object to resist changes in its motion. Whether it's staying still or moving, it just wants to keep doing what it's doing. This resistance is what we call inertia. Now imagine you're rolling a bowling ball down the lane. The ball will keep rolling in a straight line at the same speed. It'll keep rolling until it hits those pins, or the friction from the floor slows it down. Friction is an external force that acts against the motion, gradually slowing the ball. See, without those external forces, your push or the friction, the book and the bowling ball would just keep doing what they were doing. They wouldn't change their state of motion on their own. It's like they're saying, hey, we're comfy here, we're not moving unless you make us. So, next time you see an object just sitting there or moving steadily, remember it's just being a couch potato, sticking to its inertia. And just like us on a lazy Sunday, objects need a little nudge to get going or to stop. That's the beauty of Newton's first law of motion. It explains why things don't just randomly start or stop moving. So whether it's a book, a bowling ball, or even a planet, everything follows this simple yet profound rule. Inertia is everywhere, and it's what keeps the universe in a delicate balance. Now let's dive into Newton's second law, a fundamental principle that explains the intricate relationship between force, mass, and acceleration. This law is a cornerstone of classical mechanics and helps us understand how objects move and interact. This law is elegantly summed up in a neat little equation, F equals ma, where F represents force, m stands for mass, and it denotes acceleration. This equation is not just a formula, it's a powerful tool that allows us to predict and analyze the motion of objects. In simpler terms, this equation means that the more force you apply to an object, the faster it will accelerate. This concept is crucial in understanding everyday phenomena and engineering marvels alike. Think about pushing a shopping cart versus pushing a car. The difference in effort required is a perfect illustration of Newton's second law in action. You need way more force to get that car moving because it has a much larger mass. This is why heavy objects are harder to move. Their greater mass requires more force to achieve the same acceleration as lighter objects. And acceleration? That's just a fancy word for how quickly an object's velocity changes. It's a measure of how fast something speeds up or slows down. So the harder you push that shopping cart, the faster it will accelerate, and the quicker you'll be zipping through the grocery store aisles. This is a practical example of how force and mass interact to produce acceleration. But here's the catch. If you apply the same amount of force to a heavier object, it won't accelerate as quickly. This is because the object's mass resists the change in motion. It's like trying to push a sumo wrestler versus a feather. The feather will go flying with the slightest nudge. This law is everywhere, governing the motion of everything from the smallest particles to the largest celestial bodies. It's why you need more force to throw a heavier ball. The mass of the ball determines how much force is required to achieve a certain acceleration. It's also why rockets need massive engines to overcome Earth's gravity. The enormous mass of the rocket requires a tremendous amount of force to lift off and accelerate into space. and why even a tiny sneeze can send a speck of dust flying across the room. The small mass of the dust particle means that even a small force can produce a noticeable acceleration. Newton's second law is a powerful tool that helps us understand and predict the motion of objects in our everyday lives and beyond. Chapter 3, Action-Reaction, the universe's boomerang effect. And finally, we arrive at Newton's third law, the one that's often quoted but not always fully understood. For every action, there is an equal and opposite reaction. This fundamental principle is a cornerstone of classical mechanics and has profound implications in our everyday lives. This means that whenever one object exerts a force on another object, the second object exerts an equal and opposite force back on the first. It's a dance of forces, a constant push and pull that keeps the universe in balance. Let's say you're floating in a swimming pool and you push off the wall. You might think it's just you moving forward, but there's more to it. You move forward, right? That's the action. Your muscles contract and you push against the solid surface of the pool wall. But what you might not realize is that the wall also moved just a tiny bit in the opposite direction. The force you exerted on the wall caused it to exert an equal force back on you. That's the equal and opposite reaction. This interaction is subtle but crucial, demonstrating the interconnectedness of forces. Or think about firing a gun. The mechanics of this action-reaction principle are even more evident here. The bullet shoots out of the barrel with a powerful force. That's the action. The explosion of gunpowder propels the bullet forward at high speed, but the gun also recoils backward, pushing against your shoulder. That's the reaction. The force exerted on the bullet is matched by an equal force pushing the gun backward. This law is why we can jump, why birds can fly, and why rockets can blast off into space. It's the principle that allows for movement and propulsion in various forms. When you jump, you push down on the ground, action, and the ground pushes back up on you with an equal force, reaction, propelling you upward. This is the same principle that allows trampolines to work, amplifying the forces involved. It's like the universe has this built-in boomerang effect. Every action you take creates a reaction somewhere else. Pretty cool, right? This interconnectedness of forces is what makes the universe such a dynamic and fascinating place. From the smallest particles to the largest celestial bodies, everything is in a constant state of action and reaction, shaping the world as we know it. So, there you have it, Newton's 3 laws of motion, explained in a way that even your pet hamster could understand. We've learned that objects like to keep doing what they're doing, inertia, that force, mass, and acceleration are all connected, and that for every action, there's an equal and opposite reaction. Now that you're armed with this knowledge, I challenge you to start noticing these laws in action in your everyday life. Pay attention to how objects move, the forces at play, and the reactions they create. If you enjoyed this cosmic journey, give this video a thumbs up, share it with your friends, and subscribe to the channel for more mind-expanding explorations of the universe and beyond. Until next time, keep those brains buzzing.